Okay, so with confidence intervals behind us, we are ready to move forward. We're ready to proceed, and we're going to start talking about the second type of inference that we mentioned, which is hypothesis testing.
In review, sometimes as researchers, our goal is to come up with an estimate or perhaps a range of estimates for some unknown population parameter, such as the population mean mu, or maybe the population proportion p. We can accomplish this. We can accomplish this with point estimates. Point estimates is just a fancy name for our best guess. So the sample mean, we would say, is a point estimate for the true mean or the population mean. The sample proportion is a point estimate for the population proportion. But even more importantly, we can accomplish this by coming up with a range of plausible values for this parameter. So not only do we come up with the best guess, but we might say, I think that the true mean, I think the population mean is somewhere within this plausible range with a certain level of confidence. This is exactly what we've been talking about. This, of course, is the confidence intervals that we already have discussed and gone on to master.
However, sometimes our goals are slightly different. Sometimes our goals are to test whether an unknown population parameter, such as mu, such as the population mean, to test whether it's larger than some number, perhaps to test whether it's smaller than some number, or, right, a third possibility, to test whether it's different than some number, right? Some fixed value, some actual number that we're going to sort of, in its general form, call mu naught. So that little 0, right? 0 is like nothing, and so there's that word NAUGHT where it's not, where they say, oh man, all that hard work and it was all for naught, right? That means it was all for nothing. So we verbalize that as mu naught. This is called significance testing in our book. To just about everyone else in the world, it's called hypothesis testing, and it's the goal of the remainder of this chapter, for the entirety of this chapter. Chapter 6 is dedicated entirely to hypothesis testing. So what is hypothesis testing? Hypothesis testing is quite simply trying to pick between two competing hypotheses. The first hypothesis is called the null hypothesis. It's denoted by h sub 0, or like I talked about last slide, we more commonly refer to that as h naught. The second hypothesis is called the alternative hypothesis. It's denoted by h sub a, right? So these are like just abbreviations, right? Instead of writing out null hypothesis over and over and over, we just write out h sub 0, right? H naught. Instead of writing alternative hypothesis over and over and over and over and over, we just write h sub a. Now, just to warn you, sometimes some books, and perhaps even myself at some point, instead of using h sub a, they just do h sub 1. So there's maybe a couple ways of denoting the alternative hypothesis. I'm going to try to consistently use h sub a, though. So, the null hypothesis, h naught, is usually a pre-existing statement or claim. The null hypothesis is usually the status quo, or a statement of no difference or no effect. It's typically that some unknown parameter of interest, right, perhaps at least to start with the population mean, equals some value mu naught. Right? For just dabbling in hypothesis testing, the null hypothesis will always be a statement of equality. It's always going to be that some parameter equals some number. So for example, right, this is just a very terse, symbolic way of writing that the null hypothesis is that the population mean is equal to 60. That's what the mu naught colon mu equals 60 is saying, right? It's just tersely, compactly expressing what's written in that bottom line, that the null hypothesis states that the unknown population mean is equal to 60. Now, the adversary of the null hypothesis is the alternative hypothesis. The alternative hypothesis is a claim about in which way, how it is, right? It's not only a claim that the null hypothesis is wrong, it also specifies in what way it's wrong. And there's three possible ways of sort of refuting the null hypothesis. So, there's three cases that we need to consider, and these three cases are going to become a prevailing theme throughout Chapter 6. We need to be sort of cognizant of their existence, and we need to be aware of their distinction. So the first case, the first possibility, is to say, no, I don't think the mu is 60, I think it's something less than 60. It's one possible alternative hypothesis. Another alternative hypothesis is to say, no, I don't think the mean is equal to 60, I think it's more than, I think it's larger than 60. The third possibility, the sort of third contradiction, is to say, no, I don't think the null hypothesis is 60, I think it's literally not 60. Could be more, could be less. Now, these first two tests are often called one-sided or one-tailed tests, right? Because we're only interested in the mean being one direction from that mu naught, right? In the first case, we're only interested in whether it's smaller. In the second case, we're only interested in if it's bigger. The third case, we call it a two-sided or two-tailed, because we're interested in both directions. We're interested in the possibility that the mean might be either more or less, right? Both directions away from 60. Right? So this is just reiterating what I said. I thought it might be easier for me to say it while you could actually see the actual hypotheses written down. So, let's do a couple cases. Let's look through three examples, and in each of these examples, we'll actually write out what the hypotheses are. So that's the first thing that we need to be able to do. We need to be able to take a word problem, right, an actual sort of research context, and we need to be able to, right, based on the objectives, right, based on the missions or goals of the researcher or the problem, write out what the actual hypotheses are. So, McDonald's claims, I believe, if you go on their webpage, that the Big Mac has a mere 30 grams of fat. Now, is McDonald's claiming that every Big Mac has 30 grams of fat? No. Not even McDonald's has that level of exact control, right, on their burgers. Some Big Macs are going to be a little fattier than 30 grams. Perhaps some Big Macs are going to be a little less fatty than 30 grams. What McDonald's is really claiming is that on average a Big Mac has 30 grams of fat. Now, let's say that we as the FDA, right, we've been getting a lot of complaints from consumers, people writing in and saying, you know, I've been eating a lot of Big Macs lately, and it really seems like I've been putting on a lot of weight, and I'm kind of suspicious that maybe there's really more than 30 grams of fat in those delicious little burgers. And so we, as a watchdog agency, would need to test. And what is it we would be interested in testing? We'd be interested really in testing whether the mean fat content is larger than 30, right? Because that's what would be harmful to the public. If it was less than 30, then, you know, as far as the government's concerned, who cares? McDonald's might want to advertise if it's less than 30. But for someone who's just watching out for the public, we would really perhaps only care whether it's more than 30. So, we're going to show on the next slide how we would write out the hypotheses. So, here we are. Remember, it's actually sometimes easier to start with the alternative hypothesis. So, what we want to actually show, what we want to prove, what we want to demonstrate is that mu, the mean fat content of Big Macs, is more than 30. That's what we're interested in testing. That's our hypothesis. Once we have that, the null hypothesis, remember, is always a statement of equality. So the null hypothesis is going to be that the mean, mu, the mean fat content of all Big Macs, is equal to 30. Example 2. It is known that the average time to take the ACT writing test is 240 minutes. A test preparation course claims that for a mere $1,000, they'll teach students how to take the course and finish faster than 240 minutes on average. So, let's say that we approach this claim with a certain amount of skepticism, and we want to test whether or not their claim is actually true. Well, in this case, right, their claim is that the average time it takes to finish the ACT writing exam is less than 240. So our alternative hypothesis is going to be that the mean is less than 240. That's what we want to test. Once we have that, the null hypothesis is always a statement of equality. So the null hypothesis is going to be that the mean time to complete the ACT writing exam for people that have taken this test prep course, well, the null hypothesis is kind of like the test prep course is not effective, in which case the mean time to completion is only going to be the overall average time to completion, which is 240 minutes. Third example. A healthy systolic blood pressure is known to be 115 millimeters of mercury. So, a group of patients are potentially unhealthy if their systolic blood pressure is something other than this, right? We want to be able to determine or catch whether it's more than 115. That's often what we focus on as a society, because I think that tends to be the American problem, right? You have like hyperthyroidism, hypertension, things like that make your blood pressure too high. But there certainly are instances where your blood pressure can be too low, and that's also bad. My grandfather, he had that issue. He had chronically low blood pressure, and he was like a nut job. He would carry like a salt shaker with him everywhere. And everything that he ate, he was constantly just dumping large amounts of salt on it, because the doctors told him that would help bring his blood pressure up. He would salt ice cream. He would salt salads. He would salt his lemonade. He was like a salty nut job. And so, right, if we want to test whether it's something other than that, well, let's go to the next slide and see sort of symbolically what the actual hypotheses would be once we set them up. So here we are, right? We want to test whether it's more or less, whether it's something than other. So our alternative hypothesis is going to be that mu, right, the average blood pressure for all patients, is something other than, is not equal to 115. The null hypothesis, always a statement of equality. In that case, it's that the overall group of patients is healthy, that their blood pressure is what it should be, or their average blood pressure is what it should be, which is 115. Easy enough? We'll see. I mean, the setting up the hypotheses is probably the most important step. And of course, the way you're setting it up, right, you're looking for little buzzwords in the problem. Words like, we're testing it's more than this, we're testing it's less than this, testing it's something other than this. Now, when performing a hypothesis test, it's possible to make two different kinds of errors. It's possible to make two different mistakes. Here's a table sort of signifying or representing this. So going along the top, the columns represent the sort of true underlying reality, the thing that we as researchers can never know with 100% certainty, but it's what we're trying to get at, right? It's that universal truth. The rows correspond to our decisions as researchers, generally based on evidence and statistical reasoning. Now, the decisions that we make as researchers are going to be one of two decisions. The language is somewhat awkward. I'm personally not a big stickler about the language. To me, it's just statistical semantics. But there is a rationale for saying it so awkwardly. I don't think it's worth spending our lecture time going into it. Again, I feel it's one of those things that detracts from the big picture or the important concepts. But there are people out there to whom the proper language makes a big deal or a big difference, and so I am going to teach you the correct way, just on the off chance you bump into these people. That way you won't get yelled at by phrasing our decision incorrectly. So, the two decisions that we can make. We could reject the null hypothesis, right? If we reject the null hypothesis, well, there's really only one other option, right? There's only one other alternative, and that's the alternative hypothesis. So when you say that you reject the null hypothesis, right, that's just a weird roundabout way of saying that between the two hypotheses you're going to pick the alternative. Now, if you fail to reject the null hypothesis, then that's basically saying that you like the null hypothesis, right? So again, we don't use this language, but that's akin to picking the null hypothesis as your favorite between the two. Now, think this through. It should hopefully make sense to you. If the null hypothesis is actually true and we reject it, whoops, that's a frowny face. Agreed? We've made a mistake. We've made an error, and we actually give that error a name. That's a not so poetically named type 1 error. Now, if the null hypothesis is false and we reject it, well, we did the right thing, right? We made a correct decision. We've earned ourselves a happy, a smiley face. Hopefully that makes sense. If the null hypothesis is true and we fail to reject it, we have again made a correct decision. We have again earned ourselves a happy face or smiley face. However, if the null hypothesis is false and we fail to reject it, well, that's a frowny face. That's a mistake. That's an error. We call that a type 2 error. Does that make sense? I like to conceptualize hypothesis testing as sort of being on a jury in a court of law, right? And as a juror, right, there's two types of mistakes you can make as a juror. Agreed? You could what? You could let a guilty person go free, right? That's one possibility. Or you could send an innocent person to jail, right? It's really the same sort of idea, right? In our judicial system, right, we're innocent until assumed or until proven guilty. Agreed? So that means innocence is sort of that status quo. Innocence is sort of that pre-existing claim. So the idea of a person being innocent is sort of equivalent to that null hypothesis. And just like in the judicial system, we require a what? A preponderance of evidence to sort of overturn someone's, right, God-given assumption of innocence. Well, in statistics, we're going to see it's the same idea. We need a large amount, a quote, preponderance of evidence to sort of reject the null hypothesis. Right? That null hypothesis, that pre-existing claim, is kind of what we're going to assume is true unless we're given overwhelming evidence to the contrary. Now, what do we mean by overwhelming evidence? That's something that we still need to talk about. That's an idea we still need to develop. But hopefully that comparison maybe makes a little bit of sense. So if we're thinking of the null hypothesis as someone's innocence, then what? A type 1 error would be what? A type 1 error would be if a person is actually truly innocent and we reject their innocence, that is, we send them to jail. That would be a type 1 error. A type 2 error is what? The null hypothesis is false. It means they're not innocent, right? And we sort of fail to reject the null hypothesis. So failing to reject the null hypothesis, that's kind of like saying of the two, we prefer the null hypothesis. So that's saying that, well, we don't see any reason to reject their innocence. We don't see any reason to send them to jail. So, awkward language, I know, but a type 2 error is essentially the person is guilty, but we let them go free. Easy enough? So, in terms of the Big Mac examples, a type 1 error would be concluding that Big Macs do have more than 30 grams of fat on average, when in fact they do not. A type 2 error would be concluding that they do not have more than 30 grams of fat on average, when in fact they do. So think this over, print up your PowerPoints maybe if you haven't already, look at how we set up the hypotheses and think this through. There usually is a question or two on my exam, and maybe even a question or two on the comprehensive final, if you're taking this in the fall or the spring semester, that asks about type 1 or type 2 errors. Now, for any given hypothesis test, there's sort of two errors that we can make. There's the type 1 error and the type 2 error. Now, the probability of making these errors is given a name. We use the Greek letter alpha, that's what that first symbol is, to denote the probability of a type 1 error. We use the Greek letter beta, it's the second symbol, as the probability of a type 2 error. 1 minus beta is sometimes called, actually often called, the power of the test. 1 minus beta is essentially the probability of rejecting the null hypothesis when it's false. So 1 minus beta, the power, is actually the probability of doing something good, which makes sense. We think of power as something that's generally positive. Now, ideally, right, for an ideal hypothesis test, we would want what? For an ideal hypothesis test, we would like both alpha and beta to both be small. Agreed? However, it's not too hard to see that as alpha increases, beta decreases. That is, alpha and beta have a negative relationship. Does that make sense? Unfortunately, I can't scroll back to the table. Maybe you have it printed out and you could take a look at it. Let's say, not saying this is the right way or a good way of doing it, but let's say that our hypothesis testing procedure is just to always reject the null hypothesis. Let's say that we don't even care. We're given a problem and we start reading it and we say, okay, we got a bunch of kangaroos and they're all lined up on our front lawn and who cares? Reject the null hypothesis. Next problem. Oh, okay, I got some patients, and they have a blood pressure, and there's some Pepsi involved, and who cares? Reject the null hypothesis. Alright, there's some sheet music, and then there's some kneecaps, and then it starts to rain, and who cares? Reject the null hypothesis, right? Let's say that we always, no matter what, always reject the null hypothesis. Which is what? It's kind of like a crazy judge who just always sends people to jail, right? Just constantly cuts off people's heads. Who's like always saying guilty, 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 guilty. Well, in that situation, right, our alpha, our probability of making a type 1 error, the probability of sending, right, an innocent person to jail is probably quite high, agreed? If your decision making as a judge is to always send somebody to jail without even listening to any sort of testimony or evidence, without looking at any sort of data or information, then, right, the probability of a type 1 error, the probability of sending an innocent person to jail is probably quite large, agreed? So this is a situation of a high alpha. But, say what you will about this process, what is the beta? It's small, agreed? In fact, not only small, it's 0. The probability of making a type 2 error, if you always reject the null hypothesis, think this through, it's important. The probability of making a type 2 error is 0, right? If you always send people to jail, no matter what, right, the probability that you let a guilty person go free is 0, isn't it? Which is what I'm trying to say. When your alpha is large, your beta is small. Which is unfortunate because we want both of them to be small. But by making one small, what we're saying is that the other one, in a corresponding way, goes up. Thankfully, we can get around that. We can get around that because there's a third factor that comes into play. One that we as researchers have some control over, and that's the size of our sample. So, classical hypothesis testing starts like this. We will continue with the details in the next PowerPoint. But classical hypothesis testing starts like this. We generally fix a pre-specified level for alpha. We generally decide ahead of time what our alpha is going to be. It's generally accepted that the alpha is more important than the beta, so it becomes our starting point. Usually our alpha, right, this is sort of the probability of a type 1 error, right? The probability of sending a innocent person to jail, right? We make that probability to whatever we're willing to live with. That value is often 10%, 5%, or 1%. If you work for the FDA or government, you're mandated that it's 5%. So most often it's 0.05 that is used. Once we've selected our alpha, a lot of researchers actually stop there, but ideally what you should do is then you should decide what your ideal beta is. And there's not really a universally accepted beta, but again, ideally you want it to be low, maybe something like 5% or 10%. And then what you have to do is you then have to use some equations that are a bit complex and beyond the scope of this class, but they exist and they're out there. Use some equations to figure out what sample size you need to get the beta you desire, right? So you might say, I want my alpha to be 0.05, I want my beta to be 10%, and you might say, well, to do that I need a sample size of 500, which is more than I can afford. Which means that you would have to what? You would have to compromise on one of these. Generally that alpha, like I said, is seen as more important. You wouldn't compromise on that. You would just say, okay, I need a 500, sample size of 500 to get a beta of 10%. I can't afford that. I can afford a sample of, say, 200, and that's going to give me a larger beta. I'm just going to have to live with it. So, to sort of flesh out this process further, well, that's what we're going to do in our next PowerPoint. So looking forward to seeing you then.